Hello, I am Jody Wolf. You're watching Expoz today, February 18, 2016, 4:50 a.m. in Birmingham. Topic right here, I'm going to do my very best to explain exactly what Crispr is, how it's introduced, some things here not mentioned but very obvious. So they did leave out some, and I know this. And then I'll lead you or let you hear what she says, 5 different stages. But I want to show you during that time 2 things. High technology, guys. It's going to really be high technology now. But they can't keep up with me. This is why I'm doing it this way. First, let me get started on what this lady is talking about on the CRISPR. So here we go.
Once those bits of DNA have been inserted into the bacterial chromosome, the cell then makes a little copy of a molecule called RNA, which is orange in this picture, that is an exact replicate of the viral DNA. RNA is a chemical cousin of DNA, and it allows interaction with DNA molecules that have a matching sequence. So those little bits of RNA from the CRISPR locus they bind to protein called Cas9, which is white in the picture, and form a complex that functions like a sentinel in the cell. It searches through all of the DNA in the cell to find sites that match the sequences in the bound RNAs. And when those sites are found, as you can see here, the blue molecule is DNA. This complex associates with that DNA and allows the Cas9 cleaver to cut up the viral DNA. Makes it very...
Okay, that's her describing how it works. Now, here we go on how it's introduced at this point. And a little bit more right here.
Precise break. So we can think of the Cas9 RNA sentinel complex like a pair of scissors that can cut DNA. It makes a double-stranded break in the DNA helix. And importantly, this complex is programmable. So it can be programmed to recognize particular DNA sequences and make a break in the DNA at that site. As I'm going to tell you now, we recognize that that activity could be harnessed for genome engineering to allow cells to make a very precise change to the DNA at the site where this break was introduced.
Okay, that's where they introduce it. The next point is I have to go to another time. It's closed. Right here, this is only 24 seconds worth.
DNA. And these technologies were very promising, but the problem was that they were either inefficient or they were difficult enough to use that most scientists had not adopted them for use in their own laboratories or certainly for many clinical applications.
Okay, and there she is. She's given a slight warning at this time. And then we go forward just a little bit more. And on this part, she's going to tell you what it could do. And also the delivery through blood.
New piece of software. Whereas the CRISPR technology is like software for the genome. We can program it easily using these little bits of RNA. So once a double-stranded break is made in DNA, we can induce repair and thereby potentially achieve astounding things like being able to correct mutations that cause sickle cell anemia or cause Huntington's disease. I actually think that the first applications of the CRISPR technology are going to happen in the blood, where it's relatively easier to deliver this tool into cells compared to solid tissues.
Okay, there she mentions that. Now, there's 30 more seconds here before I get to the last part. And this will give you a little more anyway, it's discussing engineered humans, kind of what it can do on up front, and they've just touched the tip of the iceberg.
But we have to also consider that the CRISPR technology can be used for things like enhancement. Imagine that we could try to engineer humans that have enhanced properties such as stronger bones or less susceptibility to cardiovascular disease, or even to have properties that we would consider maybe to be desirable, like a different eye color or to be taller, things like that. Designer humans, if you will.
Okay, and what she's describing there was designer people like me. So let me move on a little bit more, and then I'll do my spiel. And so let me get started right there. This is the warning.
This raises a number of ethical questions that we have to carefully consider. And this is why I and my colleagues have called for a global pause in any clinical application of the CRISPR technology in human embryos to give us time to really consider all of the various implications of doing so. And actually, there's an important precedent for such a pause from the 1970s when scientists got together to call for a moratorium on the use of molecular cloning until the safety of that technology could be tested carefully and validated. So
there we are. This is the lady, and I'm going to have the name and the site and everything up for you. But I'm high tech. They'll catch up with me one day. You take a normal strand of DNA, take a whole scale railroad track, lay it out. You know, it's got the track bed, which on rail trains, they're 8x8 blocks, Chris, so, you know, they can carry hundreds of tons. And you take that DNA strand and start twisting it, then you can start tying knots in it. You can do anything with it. But the point and the key is, where are you going to insert the new DNA? What you have is a liar DNA. This is the Cas9. This is the CRISPR. It's the liar. It tells the DNA, hey, we have a copy here. Don't worry if something happens to you. So you have the red RNA. It is a copy of the DNA who was broken right here, moved out of the way, and then while the DNA is trying to protect itself, then the RNA steps up and says, hey, we got you covered. We duplicated the part that was taken, so it slips in here. Well, the DNA is still not happy. It's trying to kick it out. Well, then you have the Cas9. Cas9 forms like a callus around it with brain waves. And this callus is protecting the area that was just damaged. So what I see is a DNA compromise. Cas9 tells DNA it's okay. RNA copied it. It's a copy of the DNA to be replaced. Replace the broken strand. But the Cas9 told the RNA it's okay. The new man produced DNA is asserted, and now the end result is he is no longer God created fully DNA. This is what happened in the days of Noah. This is what happened in the days of Nimrod. This kind of infected people that had not all human DNA is the reason many cities were destroyed, like Sodom and Gomorrah. They were destroyed by many different reasons. Sodom and Gomorrah, sex. Not sex on the beach, but sex in the sand, everywhere. even put a bed in the street because a Supreme Court judge said it was okay. So they had to be destroyed. They were not fully human. God had to destroy them. So as in the days of Noah shall it be in the days of the coming of the Son of Man. How will this mark get in your right hand or in your forehead? I got it figured out. Earlier I said, simple, the Cas9. Just inject it. And it automatically snips that DNA and allows the RNA to insert a temporary piece until man can finish inserting what he wants that to be. That's not the real problem. The real problem is when you have something inserted in you that will control that DNA that was spliced into you into doing what it wants to do. This grain of rice here or in your forehead is monitored by whoever the government is. You are controlled from anywhere around the world they so desire. This is the break from God-given DNA to man-created DNA. And then this grain of rice or salt or however big it is that's put in there is going to be the engine. It's going to be the computer that changes that program anytime it gets ready. Look, what I have has merit to it. You know it. Just think about that. She said in 10 years, this will be fully implemented and used everywhere. I believe that. And I believe it'll be quicker than that because they are far more ahead of what they want us to believe. But here you go. That's my idea. I won't repeat it, but you got it. Jody Wolf Exposed.